Good morning, everyone. So I don't know whether I should greet you in English or there's more French-speaking people here, Arabic people. So anyway, so today we have Yousesef Azouzi, who's from Tunisia University of Carthage, if I got it correctly. And there's a number of students, or another number of people who are visiting. We are honored with their presence in the university. We've done a few seminars and so on presented by them. And just to continue the tradition, we have Professor Azouzi who will give us the talk in this week's talk in the CoE. I think most people, thinking more to the outside and so on, are aware of what the center is. The Center of Excellence, for the benefit of those outside the university, is a center that's been established by the NRF, the National Research Foundation, although it is housed in at this university, but it's actually a national body that represents a number of universities, something like 20 universities.
Thank you all. Thank you, everybody. It's easy to talk to you in this university. It's my third time that I came here. So the talk is about nets, and I have changed it several times because it depends of audience. I'm working on vector lattices, binary lattices, structures of order. But I think that a few people work on this area. So the most of my talk will be concerned with the topological stuff. One of my purposes is to convince you of the importance of nets, that they are useful, important, and we can do things easier with nets. So I start with some motivation. So in metric space or in knowledge space, we are used to work with sequences. So sequences are easy and standard tool. And if we have a sequence, this means that we have a map defined from n to some set. And now, if we want to describe the fact that X belongs to the closure of some set, we can use sequences and balls. So every ball of center X and radius 1 by n meets the set A in some element E, xn. And then we can construct a sequence which converges to X. It becomes closer and closer. So the ball becomes smaller and smaller, and the sequence becomes closer to the point X. We can describe continuity, compactness, everything in terms of sequences when we work in metric spaces. But if we work in some more general situation, topological space, so we don't have sequences cannot express this kind of continuity compactness. I will give later an example of compact space such that we can construct a sequence having no cluster point, having no convergent subsequence. So we need more general things. So we can replace more general things, neighborhoods. And for neighborhood, we can do the same thing. That every neighborhood, if we take an element in the closure of a set A, then every neighborhood meets the set. And so we can, for every neighborhood V of X, we can define XV. So can we say that XV, like the sequence, converges to X as V? So here we need to give some sense to this expression. Now, if we come back to the definition of convergence, this is the definition of convergence. So for every epsilon, we can find a rank such that this condition is satisfied. And we can work with neighborhood. So we have this this property. But here, if you work in topological space, there is no ball. So if we use the neighborhood, we can find some xv. So the expression for all n more than or equal than n0 should be replaced by for all v more or equal than v0, because neighborhoods will play the role of integers. But here, when n becomes bigger, the sequence becomes smaller to the point. But for neighborhood, we need something different. So for neighborhood, we are interested in small neighborhood and not in big one. So maybe it's a coherent idea to change the order here. So for us, better neighborhood are smaller. So we change the order. So we can say that V is better than V0 if V is contained in V0. And then we can give an expression of convergence in this step. So we can obtain a definition of convergence. We can say that XV converge to X if for every neighborhood U, we can find some neighborhood V0 such that for every neighborhood contained in V0, XV belongs to U. And we write that XV converge to X. Now, we can give a more general here. Sometimes we work with two sequences, and there is some rank for the first one, another rank for the second, and we need to take the maximum. So the same idea can be work with neighborhood, but here, instead of take the maximum, we are interested in smaller neighborhoods, and we can take the intersection. So intersection of neighborhood is a neighborhood. And then we can give this more general definition of convergence. So what's net? A net is like a sequence, but we just change the index set. The index set is not the set of integers, but it's a more general things like the set of neighborhoods. And this is the formal definition. So we need a set of indices, which is ordered and satisfying these properties. So if we take two rank, we need another rank, which is more or equal than these ranks. And then we construct a map or a family. We can use the notation similar to sequences. So we can take X by XV or X alpha here. And the set A is said to be directed if it's ordered like n, but the order is not total order, and satisfying this important property in one. So this is a net. Now we want to work with nets. So sometimes, sometimes we don't need this symbol to be an order, because for order we need three axioms: reflexive, symmetric, antisymmetric, and transitive. So just two conditions are sufficient. So we don't need an order, it's called the P order. So we can drop the second condition of the definition of order. But we keep this condition that for every two ranks, we can find another. Okay, I can mention two nice books. One, the book of Folland, there is a chapter in chapter 4 and 5, it works with nets. And the book of Rand, which called the taste of topology, when nets are used. In function calculus, when several advanced results are proved, we can see them in the book of Megenson. Okay. Now I will give definition, two definitions. or three definitions of. We say that a net is eventually in some set if this set contains a tail of a net. So the set contains X alpha for alpha more or equal than alpha 0. And this is used in definition of convergence. And we say that the net is frequently in A if for every rank we can find a rank more or equal than this one, such that the net belongs to A. We can say that the net visits the set A, it visited often the set A. So it's used for definition of cluster point or subnets. So there is a generalization of the notion of subsegment. Now the definition of convergence is that for every neighborhood we can find the rank such that after this rank all terms belong to the neighborhood. This can be written in a very similar way like the convergence of sequence. Just we change n more equal more equal than n0 by alpha more or equal than alpha 0. But here we have to be careful because the order here is not total, and it's important. Okay, here we can, if we need to deal with two nets, so we need these results. So if X alpha is eventually in X and Y alpha is eventually in Y, then X alpha is eventually in Y, then the net is eventually in the intersection. A similar property for frequency. So we can use this terminology to write something simple or obvious. Okay. This thanks is now with nets we can define the courses topology. If we have a family of functions defined on a set X, and we want to construct a topology on X for which every map is continuous, then can express this by in terms of net. So X alpha belongs to X, converge to X, if and if f of X and X alpha converge to f of X. And the topology is characterized by this property. I recall that we cannot work with sequences in general case. An important case is the product topology. So we have a family of projection, and we need them to be continuous. So this is an application. In this case, we can use the same thing for the weak topology. We have a norm space or Banach space, and we define the weak topology, which makes all non-continuous function continuous, but is smaller than the norm topology defined by the norm. Even more special case, if we take the same space, so the product is exactly the set of functions from I to X. And here convergence is just one-to-one convergence. So the product topology coincides with the one-to-one topology convergence. What's about compactness? I said that compactness in general cannot be characterized by sequences. And for metric space, compactness means that every sequence has a convergent subsequence. So we need to introduce the notion of subnets. Here, the subnets are somehow different because they are indexed by another set, not like subsequence. If you have a sequence, it's indexed by n, and the subsequence is indexed by n also. But for subnets, the set of indices for a subnet may be bigger than the initial set. So we need to define a function like the same var. Sequence, the subsequence is called in general x phi of n, where phi is strictly increasing map from n to n. But here, the map is defined on another set, and it takes its value in the initial set of the indices. But this is the definition of cofinal map, and then the definition of subnet. So a subnet is indexed by another set, which is different. And when we practice using nets, we can discover several examples when we need this general fact. Okay, a very expected result that if we have a convergent net, then every subnet converge to the same limit. Can point out here that the limit can be not unique, so we need to assume outdoor condition to have the same limit. Now, for compactness, cluster point is just the limit of subnet, and we have a theorem saying that the topological space is compact if and if every net has a convergent subnet or has a cluster point. When we deal with product topology, so for every component, we can consider cluster point, and the cluster point is just, we need to have a cluster point for every component. So it's easy to prove this theorem, which is like, it's saying if you have those sequences in R2, so xn, yn, so the cluster point is xy, where x is a cluster point of xn, and y is a cluster point of yn. Same thing. Here, I give you maybe a short proof of Tikhonov's theorem using. So Tikhonov's theorem said that if all spaces are compact, then their product is compact. So we start by taking a net, and we need to show that it has a cluster point. So if we work with every component, so we deal with the compact space, and there is no problem. But we need a common subnet for all components. So if we take a set of indices, and we say that we have JF is a partial cluster point if for all indices belonging to I, there is a cluster point. If we take one index, one index it's follow from the assumption because xi is a partial cluster point. Now, the set of partial cluster points is not empty. And we can order this set with a standard order that we say that J is more or equal than N if J is an extension. So we have more, and this is where we have a cluster point. So now it's not difficult to prove that we have a maximum element by using the Zorn's lemma, and then we have to show that this maximum element, its set of indices is exactly I, the set of indices, and otherwise we can take another indices not belonging to J, and using the fact that xi is a compact, so we have a cluster point, and put them together, we get another element which is strictly bigger than the first one. There is a contradiction, so maximum. So we prove Tikhonov's theorem. Maybe if I have time, I show you another proof, which is shorter, but the argument is hidden somewhere. There is some results, some strange kind of net called universal net when things are going quickly. So now I want to give an example of compact topologically compact space which contains a sequence having no convergence of sequence. So we will construct this compact using Tikhonov theorem. So we take a product space, this space, we have X is the set of all infinite subset of N. An infinite subset of N serves to construct a subsequence. For every subset, infinite subset of N, you have a subsequence. Just we take Xn and belongs to this set. And we construct the space, this one, minus 1 and power x, so function from x to minus 1. So we define this sequence, fn of x equal to 1 if n belongs to x. X is a subset of n. And minus 1 if n does not belong to x. Okay, we will show that this sequence has no convergence. So by Tikhonov theorem, we know that the space is compact. Product of compact spaces. And now we show that it has no convergent subsequence. Assume that we have a convergent subsequence, f and k. Here the convergence is twice convergent. Okay? I've seen this before. So we need, if we want to show that f and k does not converge, we have just to find an element such that f and k of x does not converge. Just we take this x term. We take x is all, and this is nk when k is even. And then it's easy to see that fn of x is minus 1 power k, which equal to 1 if k belongs to x, and minus 1. So this does not converge. So this is a case when compactness cannot be expressed in terms of sequences. There is a notion of sequentially compact space. This notion means that every sequence has a convergent subsequence, and it's not equivalent to compactness. So here we show that compactness does not imply sequentially compact, but the converse is also false. If we have a sequentially compact space, it cannot be. We can find the example, but this example is more complicated. We use ordinals, so to construct an example of topological space, which is sequentially compact but not compact. So every sequence has a convergent subsequence, but there is a net having no convergent subnet. Okay, some questions. So it is, if we work in metric space, we take convergent sequence, we take all elements of this sequence, and we add the limit, we get a compact. So the question, is it true for nets? So we need to have some knowledge how to work with nets. We need to be careful because the set of this is general set. And there is some results that do not work for nets. Although they work for sequence. Few of them, but in general, almost everything for sequence. We need to use our what we know for sequence and apply them for nets. I will show some examples of that. So the first one is false. The second and the third are true. I will give you a short proof of one of them. So continuity can be expressed in terms of f is continuous at point A infinity, you take x at point x. If x alpha converges to x, then f of x alpha converges to f of x. Better, just we need a subnet. So it's equivalent to the fact that if x alpha converges to x, then for some subnet, we have this property. And this will be used here. So if we take, it's well known that the theorem for graph, closed graph theorem, if we have an operator between two Banach spaces, if its graph is closed, then the operator is continuous. Here, another version for topological space. Here, we assume that Y is compact. And if you compare the proof with nets, with the proof with neighborhoods and open sets, this one is better. So just if we try to prove this for metric spaces, it works very easy. And then we copy the proof for nets. So we have to show that f is continuous. So we assume that x alpha converges to x. Then f of x alpha is a net in compact space. So it has a convergent subnet. And now if we take y beta of t beta, f of t beta, it's a net in the graph. So since the graph, which converges to xy. And since the graph is closed, y is equal to f of x. And we are done. But using this previous property, we need just to prove that the result is true for the subnet. Of course, we have a version for sequences. So sometimes it's useful. We can read some papers when we arrive to show that xn converges to x, and then we can just extract the subsequence f of xnk converges to x. And it's okay. You don't need to continue to prove the continuity. Okay, now it's another application. So the classical result in function analysis, saying that in Banach space, the unit val of x star is the dual of x, is compact with the weak star topology. And I present a proof with nets. So we take a net in the ball. Then, as before, it's just an application of Tikhonov theorem. We can find the subnet which converges pointwise. And if we have a sequence or a net of operators which converge pointwise, linearity is conserved. It's an easy thing. So it's linear, and we have the inequality j beta of x less or equal than the norm of x, because j beta is in the whole, and we take the limit, so we get j beta j of x less the norm is less or equal. So j belongs to the whole, and we are done again. So it's a natural way to prove compactness using nets. We can, if everything is separable, we can use sequences, and it's easy. We are used to use sequences. So if it works with sequences, we can copy the proof and change sequence like that. Subsequences. I give you another example of classical result of Azouzi, showing that if you take a subset of C of x, when x is a compact space, then give a characterization of compactness. So compactness is equivalent to closed and bounded. It's needed. And then we add another condition that it's equicontinuous. So the proof is natural. So we start with a net. We can start with a sequence because we work in normal space. But after that, we need something on net. So I work with nets because they are equivalent for normal space. So As before, we can prove that it converges pointwise using the Tikhonov theorem, because for every x, f alpha of x is bounded, so it belongs to some segment. Then we take the product is compact by Tikhonov theorem. So we have pointwise limit. First, second thing, we show that the limit, the pointwise limit, is continuous. Is just an easy task. So we use this inequality, and we use the equi-continuous properties. So we can find the neighborhood such that for J beta it's okay. So if any two elements belongs to J beta, so the beta is less or equal than epsilon. If some epsilon is fixed, then we take the lim sup to get this inequality, and this show this neighborhood obtained by the equi-continuity, it can be good for the continuity of J. Next, we show that we have the convergence, not pointwise convergence, but convergence in C of x. So again, we use net. If there is not convergence, so we can find some subnet and some point x, x gamma, such that we have this inequality, and then we obtain a contradiction by this. We have to choose. We use the equi-continuity, and this is proof. So the proof works. If we try to prove that for sequences, it works, but for sequences, we have, if we take the sequences, and for every point, we have convergent subsequence. But the subsequence depends on the point. And so here we use Tikhonov theorem, or if you some proof in some books used the diagonal process, but they worked with countable set. But we can use Tikhonov theorem and work with all elements, so we can directly prove the existence of subnet, not subsequence, that converges pointwise. For this reason, I start with the net, because if I start with the sequence, I need to work with nets after that, because I will use Tikhonov theorem, and Tikhonov theorem for topological space is true for nets, not for sequence. Okay. Now I move to. So I give you 3 examples. There is many others showing. We can show that theorem for if T is you have a compact operator T, then T star is compact, and the converse is true. And we can show both directions directly without nets, with nets. I claim that the proof is easier than the classical one. Okay, here we move to I want to mention that when for teaching when we start by teaching the notion of convergence, the notion of convergence is epsilon delta. That's it. And it's a strange thing that in fact, if we teach convergence using order, it's more simple, because the notion of supranom is more simple than the notion of convergence. If you have a set, the supranom is an upper bound, and there is for every other upper bound is more or equal than this one. So this notion can be understood by students more easily than the notion of convergence. It seems to be not natural. So for all epsilon, there is this delta. So we need more time to deal with the notion of convergence. So here the notion of order is more natural, more simple. If we work in order space, we have a vector lattice and we have an order, which behaves very well with algebraic property. And for every two elements, there is a supreme and anti. Then we can define x plus, x minus, and the absolute value like this, like for function, or like R. All noun function spaces are vector lattices, so we deal of functions with matrix order, LP spaces, spaces of continuous function, etc. Now we come back to nets. So here I have to say that convergence here is not topological. You have to be careful because the notion of closure, many notions are different. So the closure of a set can be not closed. Because what is the closure in topological space? Just we add the limit of all convergent subnet. And if we do the same thing for order structure, it's not closure in G. So here we use order to define convergence, and it's more simple. So we can define a very basic fact. What's increasing sequence? Say that x alpha is increases to x if it is increasing and x is supreme. The same for decreasing. For finite subset, we have a supreme by definition, but for unfinite subset, we do not. Maybe we do not. So here I will define the convergence. Yeah. Okay. So for increasing things, it behaves very well with algebraic properties. So now the definition of convergence. So it's there is a long story about convergence of nets in vector lattices. Until 2005, people used another definition. So this one is somehow a new definition, and now it's used everywhere. So the net here we say that x alpha is order convergent to x if there is another net. Sorry, here Z gamma, not Z alpha. So for the net Z, we choose another set of indices. So Z gamma plays the same role of epsilon in the convergence of function or real on spaces. So Z gamma plays the role of epsilon. So for every epsilon becomes for every gamma, we can find the rank after it. Everything is well. So x, the absolute value of x alpha minus x is less or equal than Z gamma. If we take the same index set, we get a less general definition. So there is a long story which compares these kinds of definition. So we can define continuity or order continuity in a usual way. Then can show that limit is unique. The limit for it's very fast. For the sum, for the supremum, for the infimum, so for the lattice and algebraic property, it's okay. And the limit infimum and its supremum are used in measurable space or in real sequences. So we have here a similar definition, but we need to assume some condition on the space. We say that the space is like R, is order complete. This means that if we take a set having an upper bound, so it has a circle, and the same similar property for the amplitude. So we can define these objects, and we get a similar result like for real sequences or real nets. Here, everything can be defined for in a similar way for sequences. So in order complete vector lattice, if we have a bounded net, bounded in order, so we have this equivalence. And we can define, of course, Cauchy sequence. Here, Cauchy means that it's used also in topological space. So for topological space, we can speak about Cauchy property and complete space. Of course, with using of nets and not sequences. So we take x alpha minus x beta, and the index set is the product of A and B. So here, if the space is not order complete, we can take its order completion denoted here by x delta. So any kind of completion is to construct a superspace which is a smaller one, the smaller one, having the property of completeness, like for metric space or for normal space. So you have this equivalence. So now, if the space is not complete, so we cannot define the Lipschitz and Lim1. But if we want to use them, we have to move the completion space and work with Lipschitz and Lim1, and then come back to the space, and we have equivalence between the components. Okay. Just a remark here. This theorem, the first one, shows that the dominated net seen before indexed by another set can be indexed by the same set if we work in the complete or the complete space. So it's usually beautiful to work in complete spaces. Okay, now we can define several kinds of properties. I didn't give here the details, but just there is a kind of density. With the order. So we take a positive element, then we can find another still positive element less or equal than x and belong to the space. This density, also there is a recent result showing that these two kinds of density are not equivalent. The first definition, for every element, you can find positive element, you can find an element between this 1 and 0. And the second, using nets. Using nets means that we say that y is dense in x if for every element x in x, you can find a net in y that converges in order to x. So if you look at the paper of Trotsky, Gao, and examples, very nice paper dealing with several kinds of convergence, order convergence, and relates them to classical one. I can mention here that all the convergence for sequences is exactly the convergence in LP for almost everywhere, but we have to dominate all sequences by fixed element. The convergence almost surely of sequences in measurable spaces are exactly the convergence, unbounded order convergence. I will give how many times I have. Okay, there is a notion of regular also. Okay, I skip this.
Five. Thumbs up.
Okay. Okay. This kind of unbounded convergence, it's an old stuff, but before just we have the definition. in recent years, we have many papers on this notion, because it's a notion that is the generalization of almost every kind of convergence. So the definition is here. So we can truncate the order convergence is x alpha minus x converge to O. And we can show that easily, that if a net converges in order, it is bounded or has a bounded tail. But if we work with random variables and use convergence, almost surely they need not be bounded. And so this notion, for if we apply it for the order, the pointwise order, the natural order on measurable spaces for sequences, we get exactly the convergence almost surely. If we change the absolute value by the norm in LP spaces, then we get exactly the convergence in measure or in probability. If we change the convergence by weak convergence, you can find another kind of unbounded weak convergence, which can give us many important results. So the first thing is to make the net bounded and then converge. Okay, this is the definition. It's also for small LP spaces. It's exactly the pointwise convergence. Notion is a very important notion because it gives us some generalization of known kinds of convergence. We can define UO Cauchy, UO means unbounded order, and UO completeness, and we can show that the UO completeness is in fact related to two kinds of completeness, the order completeness and another kind called lateral completeness. We don't have time to speak about, but this result can put two different notions of completeness in one, which is the unbounded order completeness. We have, of course, a result, similar result for sequence. So, okay, now some question. If we have this standard result, if we have a xn converge to x in L1, then for subsequence we have a convergence almost sure. The question, what about net? So this result can be generalized for sequence in Banach lattice. So we have a normed space which is complete and which is at the same time a vector lattice. So if xn converges in norm to x, then we can find the subsequence which converges to norm. And the question, what about net? Another kind of question, if we work in L1, then we have the completeness in norm. But we can define a vector valued norm using the conditional expectation operator, and we can ask about the completeness of the space, but in this time using net. There is a result by recent result by Watson and Q and about completeness, but just for sequence. So there is many basic questions about nets which are open. Here, just a last thing. It's very strange thing. It's a universal net. The universal net is a net for every set. The set contains a tail of a net, or its complement contains it. And there is, for sequences, there is almost no universal sequence. If you assume that the sequence is universal, then it has to stop. It becomes constant after some time. But also we have a surprise result that every net has a universal. I repeat the definition, but universal means for every set, after some time, the net is in this set or in its complement. Because to say that we can use this notion to get a very short proof of Tikhonov theorem and others. These are some references.
I think we'll first take questions from this audience. So are there any questions?
So if I get you correctly, you said that every sequence has a convergent subsequence, but that is not the case for nets. Right?
Every sequence.
Okay, you said something. I don't know if that's correct. You said every sequence has a convergent subsequence.
Yeah.
But that is not true for nets.
Yeah, there is a space for which every sequence has a convergence, but there is some net with no convergence subnet.
So you see, my question, first of all, I want to say that for sequence, it also depends on some other assumptions, but it's not generally that every sequence has a sequence has to be bounded.
It's a bounded,
Yes.
every bounded sequence is a.
And also depends on the space, like the net also. Because for general metric space, it is not true.
Yeah, I don't say that every sequence has a convergence. I say that there is maybe. What I mean that there is space for which particle space for which every sequence has a convergence. This space is called sequentially compact space. But it's not compact. That means that there is a net in this space, topological space, having no conversion subnet. Okay, that's what I'm
sorry. Then I have another question.
Yeah.
Please, is it possible to go back to the first reference?
Ooh, reference.
Yes.
Reference page, one back.
The first ones. The reference at the beginning of your slides.
Okay. Oh, at the beginning.
Yeah, the one from the beginning. Yeah.
Oh,
The books.
Exactly.
I give 3
the
books.
books. Yes. I am confused about I, the assumption I.
number one.
That has
Yes.
X less or equal to X.
Yeah.
Is that not true?
No, we assume this is an assumption.
No, I'm saying generally, you know, it doesn't.
Yes,
follow the
A relation is a graph, so we can say that X less or equal than Y if the XY belongs to our chosen point. So we decide to choose the diagonal that X belongs, which means that X. Can I write electricity? So what's an order relation? It's just if you have the choice element, and then you decide if this point is X, Y, you decide, you say that X less or equal than Y if
Depends on the definition
Y
of the order.
Yeah,
That is what I got now. The less or equal to, is it an order or
it's not an order. I said that in the beginning, I take an order, but some authors do not assume that it's order, just these two conditions. So they drop the third condition of third assumption of order. It's not needed to assume an order. As example of that, if you work with Riemann integral, so we take some partitions, and we don't need to compare partitions, just we look at the mesh of the partitions. So there is no anti-symmetricity. Okay.
Here's a question from the. There's a question for you.
Yeah.
There on the board.
Have you considered O2 conversions and lim1 conversions? O2.
Oh, so that's not interesting. Also, this person here is sent this question.
Yeah.
Okay, asking, have you considered that?
I think that
You may want to.
I can, yeah. I think that our L2 convergence is to choose the same index net, the same index set for the dominated net. And I said that this kind of convergence is less general than the one that I considered. But yes, we can consider this. There is some results between them, some connections. There is a paper of, I think, Abramovich about it. Also, I have some recent results not yet published about it. So, for example, if we consider the closure of a set, so if we consider the closure with respect to O1, if you want, that used in the general definition, and O2, there is some connection. I show, in fact, that they are the same. So there is a new result, but not already published. But the most useful is the definition that I gave. So more useful now, and people stop to use the O2 definition.
We'll take one more question. There's nothing there. No, there's nothing. So when I think of sequences, I see points. I see a sequence of sets, I see a sequence of sets. Do the nets look like that? Because when I think of nets, I think of, English nets.
Yeah.
So is it a sequence of these kind of things?
No, it's more complicated. It cannot be seen.
But are there cases that we can define that look like that? I mean, why would they call it nets?
No, these kind of nets are different from how considered input. Sometimes, even for people use it to work with nets, they can have some confusion.
How do you see it?
Yeah, it's the notion of subnets is a little complicated and can have some mistakes.
You can have an enormous, you can have a net that has an index set that is enormous in its initial part. So it can be your objects that are in your early indices of your net. It can be an enormous collection, so they can be unbounded and very badly behaved. And then they can narrow down in different ways. So that's why things like UO convergence are important. Because a sequence, you only have finitely many initial objects in your net type object. Whereas in a net, you can have uncountably infinitely many at the beginning, in the early stages of it. So you want to know what happens in the tail of the object. Is it well behaved near the end? And then things also can happen badly at the tail as well.
Anyway, I think we'll stop there, and thank you for the talk. Thanks for the visit of the Tunisian. Thank you.